Hello everyone. In this video we're going to talk about continuous random variables. Let's begin with some examples in terms of graphs. Graphs play an important role when we talk about continuous random variables because a lot of times you might have a data set and you're not sure what it is. You create a histogram of the data set to sort of get started, and you try to look at the shape, and based on the shape, that will guide you to your next step. You might know if you have a normal distribution or an exponential, something like that. So I ask here, can you name the distribution? So here's some well-known continuous random variables, at least graphs of them. So this one in the top left, what distribution is this? Did you say the normal distribution? Then you are correct. It's got your standard bell-shaped curve, and we could find probabilities by finding areas under the curve. Okay, moving down, what distribution would you say this is? This is actually a family of curves for various values of lambda. What distribution is this? Did you say exponential? Then you would be correct. So we have the normal, the exponential moving along this way. What distribution do you have when you have a horizontal line? Let's say from A to B. Well, this is the graph of a uniform distribution, right? And the height of this horizontal line would be 1 over B minus A. And then this one isn't so well known, but you do see it in various applications. This is an example of a triangular distribution. You could see this, if you break this in half, you have two right triangles that sort of fit together. Okay, so you could see here that, when you graph a random variable and you get a continuous line, that's why we call it a continuous distribution. So here's the formal definition of a continuous random variable. We'll say a random variable x is a continuous random variable if there exists a non-negative function f of x always greater than or equal to 0, f maps the reals to the reals, and for every subset b contained in the reals, we have the probability that x is an element of b is equal to the integral over b of f of x. Now remember, this b would be a line segment, or maybe several line segments together, but you could always integrate over it, and you could integrate this function. Okay. So when we have this type of function, it's called a probability density function, or often abbreviated as a PDF. And we know there's this wonderful connection between probability and calculus. To calculate a probability over any interval AB, the probability x is between A and B is equal to the integral from A to B of f of x dx. So that's a very useful connection. And there's also many times when we want a probability of the form, the probability the random variable x is less than or equal to x. So when we want this, we use the cumulative distribution function, often abbreviated the CDF. And the notation capital F of x is always used for CDFs. And luckily, in almost every probability book, I think in every probability book I've ever seen, this notation is used. Capital F of x for the CDF. And we can find the CDF. If you know the PDF, then we integrate from minus infinity, let's say, to x, the PDF, and the result will give us the cumulative distribution function. Now, this CDF can be very useful. If you're working with exponential random variables, it's so much easier to use the CDF. You get probabilities right away. Also, many of the tables that you use in statistics are really the CDF is where the numbers come from. Okay, so here's a straightforward example. Let's say x is a continuous random variable with PDF given by f of x is some constant times 4x minus 2x squared, where x is between 0 and 2. We want to first find c and then find the probability x is greater than or equal to 1. So how do we find c? Well, we have to use one of the probabilities of a PDF, which I did not mention on the previous slide, but I know I was going to mention it here. When you integrate a PDF, that integral should be equal to 1. So you'll see in our textbook numerous examples like this. The way to find a constant like this is to sort of work out the integral, set it equal to 1, and then solve for c. Once we have that, then we could answer some probability questions like what you see here in part B. Okay, so c must satisfy this integral, as I just mentioned. Okay, we're integrating from 0 to 2, and this is basically our PDF, but we have to deal with this constant c. So I'm going to work out the integral, leaving c out of it for now. We look at the integral 0 to 2 of 4x minus 2x squared dx. So when I integrate 4x, we get x squared here, x squared, and then we'll have 4 over 2, which is just 2. And this becomes x cubed over 3, but I still have that 2. So this term becomes 2x cubed over 3. The limits of integration, x is going from 0 to 2. So when x is 2, this becomes 2 times 4, which is 8. And then this term here, 2 cubed, 8 over 3 times 2, so 16 over 3. If I think of the 8 as 24 over 3, then I know I have 24 minus 16. So I'm left with 8/3. So now I go back over and I think about this equation. This is really 8/3 c is equal to 1. So we get c is 3/8. We just take this reciprocal. So my complete PDF looks like, well, almost what you see here with the constant 3/8 out here. Now, if I wanted to find the probability that x is greater than 1, remember we know that, x is bounded up top by 2. So the idea is I set up my integral. I'm going to take the constant outside, so I get 3/8, 4x minus 2x squared. And we integrate from 1 to 2, right? Because the PDF is defined on 0 to 2. Okay, so here, since x is greater than 1, we start with 1. But I only go up to 2. So now I go ahead, work out this integral. The algebra is pretty much the same thing that we had in part A. So now I have 3/8, and I have this expression. I evaluate from 1 to 2. It's a little bit of tedious algebra in here, but it does work out to be 1/2. You may want to try that, but the algebra should give you 1/2. Okay, let's take a look at the exponential random variable. In our textbook, they like to present things in its most general form, so they don't really get into the named continuous distributions until later on in chapter 31 or so. But the exponential comes up so much, and it serves as such a good example. So basically, in this section 24, what you're going to see are polynomials. You could use as many different possibilities for polynomials, but I wanted to pick one of the well-known ones. So we'll talk about the exponential here. You'll see a little bit of the exponential even in the book, but then they cover it in more detail later on, section 31 or 32. So we'll say that x is exponential with parameter lambda if it has a PDF that looks like this. F of x is equal to lambda e to the minus lambda x. Okay. So you're probably, when you actually see this, used to seeing this lambda as some sort of fraction. And then up here you get the same fraction. Okay, and by the way, there's this relationship. Lambda is equal to 1 over the mean. Okay, so you do have that relationship. If you solved it for the mean, you get the mean is 1 over lambda. All right, so that'll come up more so later. But what I want to really focus on here is that for the exponential random variable, the CDF, right, which is sort of defined as the probability random variable x less than or equal to x. We could get it by finding this integral. We would integrate a function like this. And when we do it, put in the appropriate limits and work them out, you see that we just get 1 minus e to the minus lambda x. Okay, so this gives us a nice fast way to find a probability of this form. We really, if we know it's exponential and we know lambda, right, we don't even need to find the integral if we get comfortable using this CDF. So it's another reason why I wanted to look at this here, is that to help you get comfortable using the CDF. In terms of graphs, we saw before, an exponential PDF, when we graph it, has that exponential decay. But the CDF, right, if you graph the CDF, it would look like this. It would be an increasing function. And, this property here that it increases, right, as you go left to right, it's increasing, and then it flattens out at 1. This is true for all CDFs. Okay, the CDF should always be increasing. You could possibly level off, and then at 1, it definitely levels off. All right, so here's example 2. Let's say that the amount of time in hours that a computer functions before break-in is a continuous random variable with PDF given by this here. Okay, so I have lambda e to the minus x over 100, and you can see over here that this lambda isn't given, but this is given. Okay, so we have a little bit of work to do, but if you're real familiar with exponentials, you will know what this is right away. We want to find the probability that the computer will function between 50 and 150 hours before breaking down. And we'll get our answers to 3 decimal places. And then we want the probability that the computer will function for fewer than 100 hours. Okay, So if we think about this property that I mentioned before, where when you integrate a PDF, it has to be equal to 1, we could use that here. So we think about the integral lambda, integrate from 0 to infinity, e to the minus x over 100 dx. We would make a substitution here, maybe a u substitution, work it out. You guys have done a lot of that in calculus. If it's far, you might want to try it on your own. But what happens is that this integral turns out to be just 100. So we get this whole thing reduces to the equation 1 is equal to lambda times 100. Lambda is 1 over 100. Right, so this agrees with what we said before. When I have an exponential, you can see over here I get minus x over 100, and then my lambda in front would be 1 over 100. So to work out the probability that x is between 50 and 150, we could set up this integral from 50 to 150. That's one way to do it. You could also try to use the CDF twice if you wanted to. You could evaluate at 150 and then subtract what happens at 50. So when we work this out, what happens is we end up with, you can see when I work out this integral, I'll have a minus out here. Okay, and then when we put in the 150, I'll have e to the minus 150 over 100. So that'll be e to the minus 3 halves. And I have that minus out here. So I'll have minus e to the minus 3 halves. Okay. And then I have a negative out here. And then I'll have another minus because I'll have minus e to the minus 50 over 100. So e to the minus 1 half. But I had two negatives that cancel out. And so the term we get from 50 is e to the minus 1 half. So we end up with this fairly simple expression, e to the minus 1 half minus e to the negative 3 halves. And when we put that in a calculator or some technology and round off, we get approximately 0.383. Okay. For part B, we want the probability x is less than 100. So we could put in from 0 to 100 as our limits of integration. But again, here's an integral. So much easier to just use the CDF. So this is equal to 1 minus e to the minus 1 over 100 times 100. Okay, or this would just be 100 over 100. So this exponent simplifies to minus 1. We get 1 minus e to the negative 1, which is approximately 0.632. Okay, one last example for this video. So now, in the previous examples, we had the PDF, we were finding probabilities. In this example, let's say we have a PDF, f of x is 1/5 for x between 2 and 7. We want to find the CDF, and then we'd like to describe the graphs for f of x and, well, the PDF, lowercase f, and the CDF, capital F. All right, so to find the CDF, given the PDF, the key idea is to take the integral. We just want to make x the upper limit of integration. So our CDF is the integral from 2, right? I start from 2 because of this lower bound. And the thinking is x may be somewhere in between 2 and 7. We don't know where, but we just want to keep it as x of 1/5. I want to change my limit of integration to t, so I make this dt. So when I integrate 1/5, I get, excuse me, t over 5. And this is going to vary where t goes from 2 to x. So we'll get x over 5 minus 2 over 5. Or we could write it as one fraction, x minus 2 over 5, for x between 2 and 7. Okay, so now if we want to draw graphs, let's just think about f of x. F of x is 1/5, right? What kind of distribution is this? Did you say uniform distribution? Then you'd be correct, right? This is a constant. When f is a constant, you get a horizontal line. So the graph, as I've mentioned here, is a horizontal line at y is equal to 1/5. Technically, it would just be a line segment between 2 and 7. The height would be 1/5, and it would go between 2 and 7, and everywhere else it would be 0. What about the CDF? Okay, so we worked out, here's our function for the CDF. If we were to graph this, what would it look like? Well, this would be a straight line, and we could think of this now as, a slope-intercept form. So it would be a straight line going up, right? As you go from left to right, it would be going up, so it has positive slope. Slope isn't steep, it's just 1/5, and the y-axis intercept would be minus 2/5. So it would be a little bit, it would intersect the y-axis a little bit below the origin, and then it would be going up. You can see when x is 2, we would get 0. So it would be going up slightly. Okay, so this completes the video. I hope you'd enjoy the video and the next section that we'll be covering.